Hello everyone, this is Han Li from TL Education Group. Today I'm going to present you our paper, Identifying at-risk K-12 students in multimodal online environments. Hope all of you have a good journey with me. With the recent development of technologies such as digital video processing and live streaming, there has been a steady increase in the number of students enrolling in online courses, such as MOOC and K-12 online one-to-one course. However, with the statistics of some recent online surveys, people already find that the finish rate of the online course are actually lower comparing with the traditional offline classes. And the effectiveness of this online education are not as good as people previously expected due to the early dropouts. In order to help more students learn better from the online environments, the early identification of at-risk students has drawn more and more attention within nowadays education research field. There has been several prior researches focused on the prediction of dropout behavior of MOOC students. However, researches about identifying the at-risk students in K-12 one-on-one courses are pretty rare due to its new appearance. Apart from that, the different characteristics between MOOC and K-12 courses, including the way for students' interactions within the class, the study intentions, and the dropout situations make the current MOOC students dropout prediction algorithm doesn't work. In order to solve the issue, here we proposed our method to identify the at-risk K-12 students with some novel designed multimodal features and some data augmentation methods. Before we go through the details about our proposed method, let's first take a look at the characteristics we conclude for the K-12 online students. First, the modality of the data is rich. The K-12 online education platform will not only record students' study videos, but also a lot of activity logs, like the students' after-class follow-up records, and even the pre-class promotion negotiations with students' parents. Second, the prediction is running dynamically, which requires the system to make prediction for students with various lengths of the learning histories. At last, since the dropout samples are always rare compared to the non-dropout ones, the data imbalance problem is also existing in the K-12 students' datasets. After we know about all these characteristics, let's first look at the features we mined for the problem. For the in-class feature, we first extract the audio from the online classroom and recordings. After that, we used the ASR technology to convert voice into student-teacher conversation text. Then, we used our proposed conversational talk feature extractor to conduct the final in-class features. The in-class features include the prosodic and linguistic features of student studying time. Through analyzing these features, we could get well known about the students' engagement and the study status during the class. Apart from the in-class feature, we conduct another type of features based on the student's activity log within the K-12 online education platform. From the out-of-class feature, we get well known about the students' external information, including their impression to the course before the formal start, and even about some of students' comments to the recent courses. The time-variant features are the ones that correlated with the students' dynamic behaviors. For example, most of students may not tell that they are currently dissatisfied with the recent course directly, but they may decrease the course arrangement for next few days. Thus, by observing the changes of students' regular behaviors, it will help us know about whether students come up with some abnormal situations. The samples we used for our prediction task are the per-day observations. For the normal way of labeling, the positive samples will only be the last day of dropout students, and the other samples sample days for both non-dropout students and dropout students will be the negative samples. However, this normal labeling method will cause the extreme data imbalance problem. In order to alleviate such issue, we extend the positive samples in trained dataset from the last day of dropout students to the last lambda days. Lambda here is the hyperparameter. Apart from that, we use the weighted based resample algorithm to upsampling the extended positive samples. The final positive to the negative ratio we set for upsampling is 1 to 4. For the weighted resampling method, we assign a time-aware weight to each cytopositive training sample to reflect the randomness effect of students' dropout behavior. The larger the weight is, the more times will the sample appear in the resample results. The time-aware weight function is a monotonic decreasing line which represents that the closer the cytopositive to the true dropout date, the more similar the cytopositive sample to the true positive sample. To fully explore the influence of the weighted resample method, we tried 3 different types of decreasing function in our experiments. At last, we conduct our experiment with 2 months multimodal studying behavior data of 3,900 registered students who studied on Dahai, a third-party K-12 online education platform. And the average time span of the students on the platform is about 86 days, which provides us about 300,000 observation samples. We split the data into train and test part based on the students' IDs, and 80% of students was used as train, and the remaining 20% used as the test. To prove the effectiveness of our algorithm, we also set a few baseline models for our experiments. The LR represents the logistic regression, DT means the decision tree, and RF stands for the random forest. For our method, we use the gradient boosting decision tree as the base model. From our experiment results, we draw 2 simple conclusions above. For the first one, we think it's consistent with our expectation, since the model incorporates a lot of multimodal features, and the simple linear or single decision tree-based methods are not good enough to catch the complicated relationship between these features. And for the second one, we also agree that the more steps we look ahead, the more difficult for model to give the accurate predictions. Apart from the overall results, here we also perform some experiments to evaluate the effectiveness of our data augmentation algorithm. For the extended range hyperparameter lambda, we find 7-day lookback window performs the best results. And for the weight function apart, the results shows that the convex function outperform the other ones. At last, we perform a set of experiments on the different modality features. From the table, we draw the conclusion that every modality of feature is important and useful, and by utilizing all the sets of features, we could be able to achieve the best results in both prediction tasks. Well, that's all for our paper's presentation, and hope all of you enjoyed the presentation. Thank you for watching. Hope you have a good time.